Greetings 347 fans, welcome to the second video having a look at non-homogeneous differential equations. In this video we're going to examine some applications of our model systems, namely mass spring system as well as RLC circuit, which result in non-homogeneous differential equations. We saw last time that the general solution of a non-homogeneous differential equation is the general solution of the homogeneous equation plus any particular solution. In that video we also explored our strategy for finding the particular solution, which is the method of undetermined coefficients. To briefly summarize the method of undetermined coefficients, we use a general similar form of the source term, comparing that general similar form to the solution, the fundamental set of solutions to the homogeneous equation. We amend it if necessary, multiplying by t, and then determine the non-homogeneous or the solution to the non-homogeneous equation that way. Okay, so without further ado, some applications of these second-order constant coefficient non-homogeneous differential equations. Here's the first one. Let's have a look at an RLC circuit where the resistance is given by 2, the capacitance and the inductance are both given by 1, where the electromotive force E of t is given by a sine function. So here we're going to have a look at the charge across the capacitor if the initial charge is 0 and 4 rather, and the initial current or the change in charge is 0. Okay, so we'll just go ahead and start with that differential equation for the RLC circuit. So again, this is L Q double prime plus R Q prime plus 1 over C Q is E of t, yielding a second order constant coefficient non-homogeneous differential equation. I want to point out that one of the reasons I chose this example is because it's in the book, and in the book there are a couple typos in the example, so I'll go through correcting those typos and make sure we come up with the correct solution. Okay, so non-homogeneous initial value problem, the first thing we have to do is find a solution to the corresponding homogeneous equation. So let's solve the corresponding homogeneous equation, LQ equals 0. And here we're thinking again of LQ being this differential operator, Q double prime plus 2Q prime plus Q, and we'll solve that corresponding homogeneous equation first. So just like we've done before, we'll try a solution of the form e to the lambda t. Doing that, we can jump straight to the characteristic equation, which is lambda squared plus 2 lambda plus 1 is 0. This is rigged up to factor nicely, illustrating those real repeated root lambda equals minus 1. Okay, so this gives us a fundamental set of solutions to LQ equals 0, given by e to the minus t and t e to the minus t. Go ahead and turn our attention now to the non-homogeneous equation. So we'll try to find a particular solution, again just using the method of undetermined coefficients. And the method of undetermined coefficients says that we should try a general similar form. So here, the right-hand side being sine of 3t, a general similar form is QP equals A times cosine plus 3t plus B times sine. Now, comparing that to the fundamental set of solutions, we can see that definitely no part of our particular solution will solve the homogeneous equation. There's no glitch in our method here. We'll just plug in QP to LQ, right? Again, this thing up here is LQ, and see what we get. Okay, so I've left out the details there, but you can imagine that when you take the first and second derivatives and mix them up as Q double prime plus 2Q prime plus Q, you end up with a cosine term and a sine term, and what we'd like this cosine term plus this sine term to equal is 2 sine of 3t. So of course it had better be that negative 6 a minus 8b is equal to 2, and similarly we had better have negative 8a plus 6b equal to 0 cosines of 3t. Okay, that gives us a linear system. For for the A's and B's, use your favorite method to solve that corresponding linear system. You can see that A is negative 3/25, B is negative 4/25, giving us the particular solution, negative 3/25 cosine of 3t minus 4/25 sine of 3t. Okay, with that particular solution in hand, as well as a fundamental set of solutions to the corresponding homogeneous equation, we can go ahead and construct the general solution to this non-homogeneous equation. So that general solution, again, is C1 e to the minus t plus C2 t e to the minus t, which I've written here in factored form, plus a particular solution, negative 3/25 cosine of 3t minus 4/25 sine of 3t. At this point, we use the general solution to satisfy the initial conditions. Okay, so we'll return up to the initial conditions, and I won't go through finding C1 and C2, just invite you to verify that C1 turns out to be 103/25, C2 turns out to be 115/25, giving us the solution to the initial value problem of this form. Now here I plotted that, and you'll see that something kind of interesting happens, namely that our charge starts at 4 with a zero derivative. It does some interesting stuff for a minute, and then that initial solution kind of fades away and we fall into an oscillatory solution. You can imagine that, just like from before, this negative exponential term will drive the first part of that solution to 0, leaving only this cosine and sine at the end of the day. Okay, so we'll go ahead and split up that solution and call the first part, the part that goes away, is called the transient solution. Okay, so again, the transient is the stuff that goes away in time. The stuff that's left in time is called the steady state solution. So you can see pretty clearly from the graph here the transition between the transient and the steady state that occurs maybe around t equals 4 or so. That's where this exponential term eventually drives that transient part to 0, leaving behind only the steady state solution. Okay, so once again, transient solution is the stuff that goes away, whereas the steady state solution is the part that remains as time gets large. It's sort of a typical characteristic of these non-homogeneous equations, that there's a part that goes away as well as a part that remains. Okay, have a look at a second example. Here's a second example, an undamped mass spring system. Mass of 1 kilogram is attached to a spring with spring constant 16 newtons per meter. An external force of cosine of 4t acts on the mass. So here we're going to go ahead and find the response of the system if it starts from its equilibrium position at rest. So those are just 0 initial conditions on our unknown function. Okay, equilibrium position means x of 0 is 0, and rest means x prime of 0 is 0. Okay, so the first thing we'll do here is solve the corresponding homogeneous equation. In general, we want to solve x double prime plus 16x is cosine of 4t, but we'll start by solving the corresponding homogeneous equation. So that homogeneous equation is given by x double prime plus 16x equals 0. Okay, so we know how to do this. Try a solution of the form e to the lambda t. Identify the characteristic equation. The characteristic equation has roots that are purely imaginary, giving rise to fundamental set of solutions, cosine and sine. Okay, let's go ahead and now have a look at the corresponding non-homogeneous equation. Okay, to look at the non-homogeneous equation, we'll start with a particular solution that's a general similar form. This is the general similar form of the source term, cosine 4t. So here a general similar form is a cosine 4t plus b sine 4t. What we see in this case is that both of those functions will satisfy the corresponding homogeneous equation. Okay, this is again the glitch in our method, so we'll amend our guess to multiplying by a factor of t. We can see that these ones no longer satisfy the corresponding homogeneous equation. Okay, so again, just plug this particular solution in, hit it with our differential operator, and when we do that, we find that, again, this is xp double prime plus 16xp. We end up with just terms that are cosine 4t and sine 4t. So, of course, what we'd like is for this to equal plain old cosine 4t, so it had better be that negative 8a is 0, and it had better be that 8b is 1, giving us b equals 1/8. So here's the particular solution. The particular solution is given by 1/8 t times sine of 4t. Of course, the general solution is just the sum of the solution to the homogeneous equation plus the particular solution. So that's going to be c1 cosine 4t plus c2 sine 4t plus 1/8 t sine 4t. And once again, those first two terms are just the general solution of the corresponding homogeneous equation, whereas the third term is the particular solution that we found with the method of undetermined coefficients. So the last step here is to identify the family member from that two-parameter family that satisfies our initial conditions. And I'll go ahead and just invite you to verify that the solution satisfying the initial conditions is given by C1 equal to 0 and C2 equal to 0. Now, it turns out that this case we'll refer to as pure resonance. Okay, and to see why, we'll go ahead and think about this oscillatory function as an oscillatory function with a time-dependent amplitude. So again, here the oscillation part is the sine of 4t, and the time-dependent amplitude is 1/8 t. So sort of like our decaying oscillation in the unforced case here, what we have is an envelope of solutions that tells us how our oscillatory part oscillates in that envelope. Okay, so here is a graph illustrating that envelope of solutions given by 1/8 t, and our oscillatory part acts between those. The blue is just the solution. And again, you can see what happens here is that unlike all of our other cases, this case grows with time, and in fact, strictly speaking, the limit as t goes to infinity of x of t does not exist, right? This thing just bounces between 1/8 t and negative 1/8 t, kind of going off to infinity as t goes to infinity. Okay, so once again, this case is called pure resonance. How to tell if a system experiences pure resonance? So first thing is that system has to be undamped. In order to experience pure resonance, a system has to be undamped, and it can experience pure resonance when the forcing frequency is equal to the natural frequency. Okay, so here we saw that the natural frequency of the system, the frequency of the solutions to the corresponding homogeneous equation was 4, and similarly the forcing frequency was also 4. Okay, so when those frequencies are equal, our solution is said to experience pure resonance. Okay, finish off with one more example. Here is a second undamped force system, and in this case we're going to have a look at an undamped force system where the forcing frequency beta is different than the natural frequency omega of the system. Okay, so in this case we'll specifically take beta not equal to omega. So we'll go ahead and solve this differential equation, this non-homogeneous constant coefficient differential equation like we've done before, by first having a look at the homogeneous equation. So in solving the homogeneous equation, it's quick to identify a fundamental set of solutions given by cosine omega t and sine omega t. The particular solution, we'll start with the trial solution of the form a cosine beta t plus b sine beta t. We'll see that no modification is needed, right? These, because omega is not beta, do not solve the corresponding homogeneous equation. And when you plug in LXP to find a particular solution, we find that LXP is equal to cosine of beta t if b is 0 and if a is 1 over the difference between omega squared and beta squared. Okay, so this gives us our general solution to the corresponding non-homogeneous equation. It's the solution of the homogeneous equation plus the particular solution. Now, in order to satisfy the initial conditions, we'll just use x of 0 equal to 0, x prime of 0 equals to 0, and it turns out that C1 and C2 have to be given as written here, giving us a solution that's a difference of cosine beta t and cosine omega t. Now, the interesting thing happens here when we use a special trig identity to express the solution of that initial value problem as a product of sines instead of a difference of cosines. So here's the trick to do that. The trick to do that is to take omega bar to be the average of the two frequencies. Omega bar is omega plus beta all over 2, and to take epsilon to be the difference of those frequencies divided by 2. Now, one of the things that you'll notice is that when we sum omega bar and epsilon, the betas cancel and we end up just with omega. And when we look at the difference of omega bar and epsilon, the omegas cancel and we just end up with beta. So here that is that statement in equation form. Omega bar plus epsilon gives us back omega, and similarly beta is given by omega bar minus epsilon. So we can recast then our general solution in terms of omega bar and epsilon just by substituting beta and omega in terms of those sums and differences of omega bar and epsilon. Okay, so once we do that, we have the desired form cosine of a minus b. So we're thinking of this first term here as cosine a minus b, and the second term is cosine a plus b, that we can transform into sine of omega bar t and sine of epsilon t. Now, certainly omega squared minus beta squared can be factored and written in terms of omega bar and epsilon 2. And once we do that, we can express our solution here in terms of omega bar and epsilon. Now, in doing that, we end up with the ability to, again, write our solution as an oscillatory function with a time-dependent amplitude. So where this ends up being interesting is in the case where omega and beta are close but not equal to each other. So when omega and beta are close but not equal to each other, omega bar ends up being the average of those two. So in this case, omega bar is 50 and epsilon is 5. Okay, so once we have that, we can see that that you can think of this as sort of a high frequency oscillation, where that high frequency is defined by omega bar, modulated by a low frequency amplitude, where that low frequency is modulated by epsilon. So so here the envelope of solutions has frequency 5, whereas the solution inside the high frequency solution has frequency 50. Okay, so this is known as beats, and many of you have experienced beats sometime in your life. You can experience beats when you take two tuning forks that are of a similar but not equal frequency and bang them, and just Google this on YouTube. You'll hear the wah 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 sound. So this graph is what wah 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 looks like. Okay, so once again, we achieve beats if we have an undamped system where the forcing frequency is close to but not equal to the natural frequency of the system. So here we had 55 and 45, but generally speaking, if beta and omega are close but not equal, you have beats. Okay, so that's it for applications of these constant coefficient second order non-homogeneous differential equations. Hope you've enjoyed this video. We'll see you next time, and so long for now.